So today we're going to start basically the second half of this class, which is about high-dimensional expanders. So we finished, our first part, which is about standard expanders, graph expanders. Now we're going to talk about high-dimensional expanders. Now, unlike expanders, expanders is a very classical topic. It's been studied for 40, 50 years now. People understand many things about it. Well, high-dimensional expanders is a much more recent topic. It's an area that started actually in topology by works of Gromov that sort of observed that various topological properties of how more robust than what we usually imagine them to be. So, and then it sort of moved into algebra, where people were able to, first of all, give some definitions of what does it even mean to be a high-dimensional expander. It's not even clear what the right definition should be. So there's combinatorial and spectral definitions, and so people from theoretical CS have joined the party and gave other types of definitions, and the field is still growing, and there's still multiple definitions, and each one with its own applications, and it's not just there is not just one clear definition that sort of encompasses everything. So it's still this baby phase. Despite that, there have already been several very surprising, very powerful applications of high-dimensional expanders in CS, and we are going to cover one of them later on this quarter about a rapid mixing of Markov chains and how to use them to basically analyze algorithms known as Markov chain Monte Carlo algorithms, which are based on doing this type of random walks, and they only work they converge best, and usually it's very hard to analyze them, and high-dimensional expanders give a unified way to do it sometimes. So, but for the most part, what we're going to be focusing on are more of the combinatorial side of high-dimensional expanders, with some connections to theoretical CS. We will, maybe towards the end of the quarter, if we have time, we're going to briefly touch on the topological side. We will probably not at all touch on the algebraic side. So just be aware that this is a much bigger field than what we're going to show you here. But let's start with the definitions. What do we even mean with a high-dimensional expander? So really the idea that you want to move from graphs to hypergraphs. So maybe let's just define hypergraphs to begin. So the uniform hypergraph. On a vertex set V is a collection of something we're going to call D faces, which is basically, let's call this E for the edges, which is just basically E is just some subset of all the possible sets of size D out of V. So if, for example, D is 3, a 3-uniform hypergraph is just a collection of sets of size 3. Okay, so in this viewpoint, it's completely a combinatorial object. It's just a family of sets, all of them of size D. And we will typically, like in graphs, take V just to be the numbers 1 to 3 up to n. So n would typically denote the number of vertices in the graph. So maybe just as an example, let's take D equal to 3. So I have a bunch of points. And then let's say my 3 edges or 3 faces are going to be a collection of 3 points. Maybe this is 1, it's going to be another one, maybe another one. Okay. So this is a simple generalization of graphs. So graphs are sets of size, undirected graphs are sets of size 2. The uniform hypergraphs are sets of size D. So this side, there should not be any complication. And then the topological way of viewing them is to say, well, we're going to take these sets, also look on all the down closures. So if I'm going to have a set of size 3, I'm also going to have all its subset of size 2 and 1, and actually also 0. So we're looking at the downward closure of the set system. And this is what we're going to call a simplicial complex. Let's call this a d-dimensional. This is usually called pure, but we want to keep saying pure again. Simplicial complex. I'll note why it's called pure in a second. Simplicial complex. X is as follows. So X is going to be X1, XD, where XD is just some subsets of vertices of size D, and Xi, all these sets tau, such that there exists, let's say, sigma in XT. Tau is a subset of sigma. The size of tau is I. Okay, so what do we have here? So whether we call it pure because all of the maximal faces here have dimension D. In general, you can think about some mixed things where you have some, maybe you have some triangles, but you also have some edges not in a triangle. In this class, we will not allow for that, but just be aware that things exist. Okay, so, but for simplicity, we will not discuss them at all in this class. So I will not keep saying pure, but if you look in the literature, they're called pure simplicial complexes. And so what do we have here? So for example, let's look on this picture here. We just draw this again. So again, it's another example here. So we start, let's again, we're going to choose D to D3. So we're going to choose some nodes. Again, we're going to have some, so X3 are going to be all the three-dimensional. Maybe this one, and this one, and this one, and this one, let's say. And then X2 is going to be all the edges that are contained in some three-dimensional space. So that's going to be an edge. And this one, and this one, this one, and this one, this one, and this one, and this one. These are going to be the two-dimensional. And then X1 is just going to be all of our vertices that are contained in some triangle. And then we're also going to have, for completeness, X0, which is just going to be always going to be just a set containing the empty set. And that's going to be, when you can ask why do we include it, it's convenient. So we're going to add it also. So all the sets in X3 have size 3, all the sets in X2 have size 2, and so on. Okay, so this is what's called the simplicial complex. Why is it called simplicial? Because if you view it in a topological sense, then it's basically triangles that are connected by edges, and edges that are connected by vertices, and this can be indulged in some topology that people in topology, that is useful to study various types of topological questions. But again, that will not be our focus here. So just be aware this object first originated in topology, but we're going to view it from the combinatorial viewpoint of set systems. So maybe now is a good point to see if anybody has any question about this definition, because that's going to be the main definition that we're going to be working with. This is a three-dimensional simplicial complex. Now, another comment about notation, when people study this in topology, so they would usually call sets of size, they would usually shift all the indices by 1. So in their notation, this would be a two-dimensional simplex, where X2 contains sets of size 3, X1 contains of size 2, X0 contains a vertex, and X minus 1 is an empty set. So just be aware that if you view the same object in the topological world, then this would have been in topology. So let's say in combinatorics literature, it's usually called this way, but if you look at the topological literature, this will be called X2, X1, X0, and X minus 1, which is actually the right thing to do if you view it in a topological sense, what is really annoying when you want to use combinatorics, because then you say, well, xk always contains set of size k minus 1, which is annoying. Oh, sorry, xk contains set of size k plus 1, which is annoying. So we're just going to use this combinatorial viewpoint here where xk contains set of size k. It's going to simplify our life. I don't have to shift things by 1 all the time. But again, just be aware that there are two types of literature on this topic, and they're sort of off by 1, which can be annoying sometimes. So again, be aware of that. And now the main question that we want to ask ourselves is, what does it mean for a simplicial complex to be an expander? So when we studied graphs, then there were several definitions that all of them made sense. So these sort of combinatorial definitions, talking about edge expansion or vertex expansion. And there was the spectral definition, that sort of what spectral expansion, viewing this as an operator. And we saw that both of them are basically the same, right? So Shiger inequality allows to go both ways. But for high dimension expanders, it's not clear what does it mean for that to be an expander. And like I said in the beginning, there are several ways you can define even like a 3-dimensional complex to be an expander. There is the topological way of doing it, something called the topological overlapping property, that I'm not going to talk about at all, but just be aware that was the original definition. And then there are notions of edge expansion you can try to define here. But we're going to, for the most part, look on a spectral definition. But again, spectral of what? Spectral of what? Again, it's not clear. So I think one of the big advances in this field came several years ago, where people in the TCS community, in particular Eri Dinour and Tali Kaufman, realized that, well, actually, there is a very reasonable way to define high-dimensional expanders just by looking on graphs. So you can just work with graphs, but you can use graphs to define notions of expansion that make sense when you study even high-dimensional objects. So you can ask, well, what type of graphs do I have here? Well, one graph that you see here in this picture is this green graph. This is called the two-skeleton. This is just, all the points and edges, in my simplicial complex, ignoring all the high-dimensional faces. So of course, this only gives, partial information, because like we said, this completely ignores high-dimensional faces. So really what you want to do is to find a way of using graphs to define this object, even when considering high-dimensional faces. And for this, a very useful definition is the notion of a link. So a link is like a local view of some node or sets of nodes or edge in this graph. And that's going to be a very central definition that we're going to study. And the main phenomenon we're going to see that if links are locally, like the graphs are good expanders, then globally this high-dimensional complex, this simplicial complex, is also something we could call a high-dimensional expander. So maybe first let's define links. And that's going to be one of the central definitions that we see here. So links. So again, so let X, which is X0, X1, union XD, be a simplicial complex. And let's choose some phase, let's say tau in xk for some k, let's say, cat must be k between 0 and d. So we're going to this phase tau, this set of k elements, and we're going to just look on all of the faces that contain tau. So the link of tau is, we're going to call it x tau, so subscript tau. It's going to be all these faces sigma, such that sigma union tau is in X, and sigma intersected tau is empty. So what do we have here? So x tau is by itself a simplicial complex. We're going to see it in a second. So x tau is going to be a d minus k simplicial complex. So again, so what is the definition of x tau? We're basically saying take all the sigmas, all the sets of such sigma that are disjoint from tau, like don't have any shared vertices, but if I add them to tau, I get something in x. So again, let's do an example. That's going to help us out. So again, let's do the following example. Maybe again, I'm going to work with like a three-dimensional complex, and again, let me sort of assume these are going to be my faces. This one and this one for simplicity. And it's also going to have, because two-dimensional edges, we're going to have this one, and this one. Right, so this is my complex. Now let's look on the link of a node. So again, let me look on the link. Let's call this tau. So let's give them names so that it's easier to.
I think there should be diagonal edges too. Well, right?
Oh yeah, I'm missing. You're right, and I'm missing here some edges. Thank you. Excellent. So again, so just to write it, if I give you things names, so 1, 2, 3, 4. So x3 has two sets of size 3. So we're going to write 1, 2, 3, and 2, 3. First, I'm going to write 1, 2, 3 instead of set 1, 2, 3. So when I write 1, 2, 3, I will always just mean the same as the set 1, 2, 3, just so it's easier to write. So we'll do the same thing in the notes. X2 here, all this sets to contain inside it. 1, 2, 1, 3, 2, 3, 2, 4, 3, 4. X1 is going to be 1, 2, 3, 4. Okay, now let's look on the link of 1. So what is the link of 1? Well, I'm looking on 1 here. And let's just look on all the sets that contain 1 if I remove 1 from them. So first of all, you see, every set of size 3 now becomes size of size 2. Size 2 becomes size 1 and so on. So x1 is going to be basically go over all the sets. X1, 2 is going to be go over all sets in x3 that contain 1 and just add them. It's going to be 2, 3. And x1, 1 is going to be go over all sets in x2 that contain 1 and add them. So it'll be 2 and 3. So 1, you see 1 only sits in one triangle here. Locally, it only sees 2 and 3 and this edge between them. So this will be the local view of 1. This is how we define the link of 1. Now we can also look on the links of larger faces. For example, if I want to look on the link of the face 1, 2, well, you see 1, 2 here is this face here. It only sees one node here. So it's going to be a one-dimensional complex. And it's going to be just this one node, 3. Okay, so this is how we define links. So again, I think here you see both a visual way of thinking about it and also the combinatorial definition. So hopefully together they give you enough intuition about what's going on here. Maybe just to give another intuition is let's look on graphs. Look at this here. Let's look on graphs. Standard graphs. So if I have a graph of VE, then it corresponds to what? To a complex. So it corresponds to a two-dimensional complex, right? Where x1 are the vertices and x2 are the edges. Right, so if this is a graph, if I have a graph here, maybe that's my graph. So it has vertices and edges. And what is the link here? So again, let's give them a name. Let's call them 1, 2, 3, 4. What's the link of, let's say, 3? So the link of 3 is going to be a one-dimensional complex, and it's going to contain 2 points, 2 and 4. It's just going to be the neighbors of the node 1. So for graphs, the link of a node is just the set of neighbors of these nodes. And the notion of linking hypergraphs generalizes this notion to higher dimensional simplicial complexes. So again, this is a very, very critical definition. So I want to make sure that you all understand it. So if there's any question, if something is not clear, then now is a good time to ask.
Sorry, I just want to clarify that if we have an edge like a three-phase 1, 2, 3, is it necessary in the graph that we also have two-phase 1, 2, 2, 3, and 1, 3?
Yes, yes, yes.
Okay.
It's always going to be closed down.
Okay.
Yes, it's always going to be the case.
I think Shahar basically said this in kind of one of the many ways he described links, but I wanted to make it very explicit because I think it's, at least to me, it's the most intuitive and natural way to view links, which is basically to construct the link of some I face, or I guess in this case, a K face tau. You really just look at all the top level faces that contain tau, you remove tau, and then you downward close those faces. This is a way to construct the complex given by the link that I think is very natural, especially pictorially, right? You just kind of look for, okay, here's the edge, here's all the top things it's contained in. Now I'm going to remove the edge and take the downward closure of that, and that gives me the link. To me, that's kind of the most natural way to view these.
Exactly. So notice that complexes are always just defined in terms of the top dimensional faces, because by definition, the way we define it, we take all the top dimensional faces and we take the closure with respect to the downward closure. So all the subsets. And then we just partition into levels based on the subset size.
Sorry, just want to clarify. So it's not possible to have a low dimensional edge that is not contained in one of the high dimensional face.
Yes. When you have this is called a non-pure simplicial complex, and you can discuss it, but we are not going to. So we're going to assume entirely in this course that we only going to work with pure simplicial complexes that do not have this. So like if you're in a three-dimensional complex and you have a two-dimensional edge, there's always going to be a three-dimensional face containing it.
Okay.
So to some extent, it's like in graphs saying, I do not allow you to have isolated nodes. That is maybe the other side. Okay, any more questions?
Would you mind defining again, like exactly what downward closure means?
Downward closure means that I take all the subsets.
Okay, yeah.
Given a set, I include all of its subsets.
Okay, thank you.
More questions? Okay. So the main type of phenomena that we study for high-dimensional expanders is what's called the local to global phenomenon. It said that if something happens locally in links, it also happens globally in the complex. And you see, once you have links, and the links are at least two-dimensional, you cannot talk about the graphs of these links. So the main type of connections we're going to see that if all the links, if their underlying graphs are expanders, then in some sense, the complex itself is an expander as well. And we're going to basically use this as a definition, but we're going to see you can define it in multiple ways, and in fact, they're equivalent, more or less. But again, that's a picture you should have in your head. I mean, we can define expansion in various ways that are global notions that we are not going to discuss in this class. Also, at least some of them we are going to discuss on the more, but for now we won't. But they're all implied by this stronger notion that links of faces are always good expanders. Okay, that's going to be somehow the stronger notion. It's going to guarantee that. Okay, so now we want to start studying sort of these links. And my goal for the next maybe 10-15 minutes is to actually define what do we call what's called some notion of an expander here that's going to be called a local spectral expander. So that's going to be a notion of an expander that is based on the local graphs. Underline these links here. And we'll see other definitions of expanders later on in this class, and we'll see that they are connected to each other. But actually, before we do that, we need to first generalize the notion of a complex to allow weights. So you should imagine that when you have graphs, you can initially study, just standard graphs, unweighted graphs, but then you can say, well, what if the graphs have weights on them? Or if they just have weights? And this will actually turn out to be really crucial here. So we need to, from now on, just talk over, when we talk about simplicial complexes, they will always be endowed with weights. So let's write this now formally. Here's a definition. So a weighted d-dimensional simplicial complex is a pair x pi. Well, x is just going to be what we thought so far. So x is just a d-dimensional. D-dimensional simplicial complex. And pi is going to be a sequence of distributions, pi 0 up to pi d, where pi I is a distribution on the ith level. Okay. So we're going to have two things. We're going to have a simplicial complex, and then there are going to be weights on every level. There are going to be weights, and actually we're only going to allow non-negative weights, and we're going to normalize them to sum to 1, so we can view them as distribution. So we're going to have one distribution on level 0, one distribution on pi 0, pi 1 is distribution on level 1, pi 2 is on level 2, and so on. And actually, if you remember the way we define simplicial complexes, they're completely determined by the top faces. Right? The top faces completely control all the lower faces. And also we require the same thing to be true when we talk about weighted simplicial complexes. So the point is, well, how do we define these distributions? So pi d is an arbitrary distribution on the left level, top level xd. And then the way we're going to define distributions of a lower level is by the following process. We sample a top level face based on pi d. And let's say I want a distribution over the kth level, then I'm going to randomly choose a k face inside it. And that's going to be the distribution of pi k. So I'm going to define it in two different ways. So pi k is, so let's say for k 0 and d minus 1. And pi k is defined as follows. So we want to define a way of sampling sets of size k. So step 1, we're going to sample sigma from pi d. So we're going to sample a d-dimensional face, and then we're going to sample tau inside sigma uniformly of all sets all sets tau have size k. So that's going to be the process. So if I want to sample a k-dimensional face, I'm going to first sample a d-dimensional face for my distribution pi d. It could be arbitrary. And then this defines my distribution on the k level by choosing a random subset of size k. Now it might be useful to actually give like a closed form formula here. So just so that you're right. So you see that in terms of the distribution of a face tau in the kth level and tau in xk. Okay. The following thing, so we're going to basically, well, First of all, we're going to sum over all the sigma in xk that contain tau as a subphase over the distribution by the sigma. And then that's going to be the probability we choose them, and then you want to normalize.
So sigma should be an XD or in the sum, right?
Sigma should be in XD. Yep. Sigma is a top level phase, XD, thank you. And we're going to normalize by 1 over D choose K. And you can actually verify that this of indeed gives you a distribution. If I sum pi k of tau of all faces, what I'm going to get the sum of all faces of level K, but every K dimensional face is going to be inside D choose K, D dimensional faces. So it's going to be repeated D choose K times. And so this is why we need to divide by D choose K. Okay, so there are two different ways you can think about it. Okay, so that's going to be our definition of a weighted. Okay, I can try to tell it. A weighted D-dimensional simplification complex is given this way. Again, just to repeat it, you start with a D-dimensional simplification complex. You put some arbitrary distribution of its top level faces, its D-dimensional faces, and then you induce from it the distribution of all the lower dimensional faces by this type of sampling process. There's actually a different way you can view this process that we're going to use probably in a couple of weeks. It's going to be where you can actually define it in a joint way where you first sample a D-dimensional face, and you remove a random node, you get a D-1 dimensional face, and you remove another random node, from it you get a D-2 dimensional face. So you can actually use it to define a whole chain of faces from 0 up to D, where the marginal of the kth face is pi k. For now, it's not important. This will become important in about a week and a half. But when we analyze random walks on expanders, but for now, it's maybe another third way you can think about this process. Today and also next week, we will probably only care about the marginals in each level k, so it won't really matter. But then later on, we're going to start talking about the correlation between them, and then this sort of joint sample process will be useful. Okay, so again, let me sort of pause for questions. I mean, we're going to see many new definitions here. So I mean, this is why these are all new definitions and maybe not super intuitive. I think it's good that you try to internalize them and see if they make sense to you or not. So maybe again, let me just, oh, my chickens are making noise here. Okay, let me try and maybe again give some example here. Let's do an example of graph, it can be easier. It's another example here. Let's say I have the following triangle, and I give its edges weights half, quarter. What's going to be the induced distribution on the nodes? Yeah, they want to participate. Yeah. Okay. It's funny. Anyways, what's going to be the induced distribution on the nodes? Well, let's see. What's the probability we sample this node? Well, we can sample the first edge equality half, the top edge, and then we're going to choose one of its two endpoints randomly. So it's going to be 1/4. Or we can choose the edge here below. It's going to be quarter, and if we choose this specific one, is going to be 1/8. So overall, it's going to be what? It's going to be 3/8. This one by symmetry is the same. And this one is going to be 1/, yes, 1/4. Or it's 2/8. It's another thing. So we sample each one. So if we look each one of the edges touching it, we choose it with the quarter. But then the probability we choose this specific endpoint is half of it. It's going to be 2/8. So overall, we get 1. So you can make sure that this sort of is intuitive. So this blue distribution of the edges is arbitrary, and this induces a distribution of the nodes by this type of sampling process. Okay, so now what do we want to do? Now we want to take with the same, we define links. And we'll say, well, how does the weight? Now we have a weighted complex. We want to also talk about weighted links of the complex. So it's just going to be, I'll write the formulas in a minute, but it basically is going to be, you take the induced distribution over the link. Okay. But let me just write this definition formally carefully so you can see it. So again, definition, let phi be a weighted d-dimensional complex. And again, whenever I write complex, I will always mean simplicial complex, in this class. I mean, there are other types of complexes, but we won't study them. So for simplicity, just write complex from now on. So let tau be some phase in xk for some k between 0 and d. So we've seen that. So the weighted. We're going to have the weighted link tau. You disperse x tau pi tau. So again, x tau is what we saw before, just a link of tau. Take all the phases containing tau and remove tau from them. What is the distribution pi tau? Well, it's basically going to be you take the distribution over the relevant phase, but then you normalize it becomes 1. So let me just write this formally. So if I look on, so let's say I write, so first of all, let's say pi tau is going to be x tau is going to be a d minus k dimensional complex. So pi tau is going to write as pi tau 0 up to pi tau d minus k, because it's a d minus k dimensional complex now, and not a d dimensional complex. And given some phase, let's say sigma in x tau L, so sigma is a size L. So just to remind you, so this means that tau union sigma is in x k plus L, right? Like a phase, an L phase in the link of tau corresponds to a k plus L phase in the original complex. Just to make sure that this definition makes sense to you. So what is its definition? So I want to define the pi tau L of sigma. Right, so I want to define the distribution in this link on the Lth level. What is the probability we sample sigma? So that's going to be what? It's going to be basically proportional to pi k plus L of tau union sigma, except that this doesn't sum to 1. This is sort of, so we're going to normalize this by the sum of all these phases that contain sigma, so that contain tau, so that this actually becomes a distribution. So this is basically a conditional distribution. So we take sample k plus L phase, conditioned that this k plus L phase contains sigma. So it's going to be over all sigma over all, let's maybe say that tau.
Conditioned on containing tau, I think.
Then so I contain the tau, like yes. It's going to be, let's call this maybe sigma prime in x tau L pi k plus L tau union sigma prime. So again, this might seem handful. So this is just basically, so this is just going to be you sample from pi k. So this is intuitively, you sample just from pi k plus L, but you condition that whatever you get, that it contains tau, right? So again, let's just look on this graph example that we had before here. So if I look on this link here, so it sees two faces, right? This is tau, then x tau 1 contains two things, contains these points, let's call them A and B. A, B, C contains A and B. And what's going to be the probability? A, well, A is going to be 3/8 over 3/8 plus 2/8, and pi tau 1 of B is going to be 2/8 over 3/8 plus 2/8, right? So 3/5 and 2/5. So it's basically saying if you only allow to you want to sample a node here, but it has to, you know, it has to be an edge, a neighbor of C. Well, in this case, all of them are neighbors of C, so it's not really doesn't really matter here. So you just sort of take the conditional distribution. If you want to choose a node basically which is not C, and so you normalize the distribution so you actually get the distribution. So is this definition clear? Then all that we're doing here is just conditional probability, but the formulas, you know, are a bit maybe messy.
I think maybe a similar way to view it is what I said before for the links last time, is that you're still just going to get the weighted version of the link of tau. You're still just going to look at all the top level, like before we said, okay, we look at all the top level faces that contain tau, and then we remove tau and downward close. Now I'm going to say we do exactly the same thing. We look at all the top level faces that contain tau, but now they're weighted. Now they have weights, right? And they're weights that don't sum to 1. So before we downward close, we normalize those top level faces to be a distribution, right? We just divide by their sum, and then we downward close the complex and use the same downward closure as we did for, we defined this method from the top level distribution to get the lower level distributions. That's all that's happening here. We can just do it for the top level, where we normalize by the kind of total weight of all the top level faces. And then we just do the normal procedure to induce all the lower distributions. This is equivalent to what Shahar is saying here.
Yes, exactly. So notice what Max said is it's actually enough to just choose L here, just one value, the maximal value, D minus K. Right? We don't define all the weights, but the top level weight just defines all the bottom ones. So it's enough to look on this level D minus K. And actually, there's going to be something useful for us to talk about. So we're going to make the following definition that's going to be sort of useful for us when we talk about the pi. What is the probability of sampling of the length of tau? Well, it's just going to be the probability they sample sigma from pi d from the big complex that tau is contained in sigma. Right, going to be the probability that, given a random d-dimensional face, it contains sigma, and that's exactly this denominator we have. That's exactly going to be the sum of all. Let's call it another sigma prime in x tau d minus I guess k of pi d of sigma prime. Right, that's another way of writing the same thing. So you see multiple ways of writing the same thing. So hopefully at least one of them is intuitive to you, and then the rest are sort of algebraically equivalent. So again, that's going to be, we make this definition because we're always going to have this type of, denominator come up when we sort of look on conditional distributions, look at the induced distributions inside links. So now also another comment is that the way we write weighted simplicial complex is like this pair x pi, but sometimes we just won't write pi when it's sort of clear from the context, but complexes always have a weight. If you don't say what it is, then it's just going to be 1 for all the top level faces. It will not be 1 for the lower ones because they might not be regular and so on. So just be aware of it. We will always work with weighted simplicial complexes. And then the links are always going to be weighted simplicial complexes as well. Okay, lower. So, and any question on? So far we've seen sort of 4 definitions, right? So let me repeat what we've seen so far today. So we've seen simplicial complexes. talked about links. Then for both of them, we added weights. It's just a recap of what we've seen so far. So think about, all of these definitions, and now is a really good time to see if you have any questions to ask. But again, we're going to be relying on the fact that you understand these notions when we move forward. Okay. So now we're going to have one more topic that we need to define before we can actually define our first notion of a high dimensional expander. And that's going to be just going back to graphs, standard graphs, but allowing weights on these graphs. Because these weights are going to be naturally coming up from the weights in this complex. And we need to do spectral analysis for weighted graphs, not just for standard unweighted graphs. So basically, essentially everything we've done so far just generalizes once you generalize the definition in the right way. So let me just make this one sort of less definition before we go back to high dimensional expanders. So that's going to be weighted graphs. So let G be a graph with weights. So the weights are going to be, so I'm going to use a pi e. So it's some distribution of the edges. So again, basically we're assuming here that the weights are always going to be non-negative. And then we also assume the sum to 1, but that's really not going to be an important assumption, but we're always going to normalize it. And then we're going to think about them as defining random walks. So if you remember before, we were talking about random walks on d-regular graphs. And in d-regular graphs, it was easy because given a node, you go to each one of its d neighbors, equally likely. But with weighted graphs, we want to give a higher probability for going to a node with a higher edge weight. So we're going to define a random walk. So the random walk here, we have a random walk. And the probability that we go from a node V to a node W is going to be the weight, this edge VW, divided by the sum of all the edges from V to U over 1. Right, so again, one way to think about it is that we look on all the neighbors of a node V. The weights are now defined on the link. The weights are defined by the weights of the edges of the graph, and we choose one of them proportional to its weight. Okay, so far I think this should be pretty intuitive, right? Just go give higher weight to edges that have no higher probability in the distribution. And also you see this assumption that this is a distribution that it sums to 1 doesn't really matter here for this random walk, because like if I multiply pi e by 10, then both numerator and denominator would multiply by 10. It will cancel out. So the assumption that it sums to 1 is just a convenient assumption here. Doesn't make a big difference. But it is important to assume that they are all non-negative. And we'll never allow negative weights here. And then we want to look at the adjacency metrics. And it will actually be convenient, I'll explain why in a second, to transpose these adjacency metrics. So let me try to explain why. So I'm going to write the same expression as above, not as A, I'm going to be as A, I guess, VW. It's going to be pi E W over all U pi E. Okay, that's going to be my adjacency metrics. Notice that if we want to really view this as the adjacency metrics of a random walk, we have to multiply on the left and not on the right. So basically, as a random walk matrix, so if we, given a distribution, let's call this maybe F of the nodes before the walk, then after the walk, after the walk, we get F transpose A. So we actually have to multiply on the left and not on the right here. And the reason we do that is because we're going to basically view this matrix, instead of a random walk matrix, we're going to view its action on the right. And the action on the right is going to be basically as an averaging operator. So let me just write what it means. So actually, what is AF? Now, let's see. So given any function, now not necessarily a distribution. So given any function f of the nodes to R, what is AF? Well, I claim AF, but it's a function again from nodes to the real numbers. And it's a value on V is exactly going to be the average of its neighbors. So it's going to be exactly the sum over all the neighbors W of V of, this probability. I copy the same formula again. This is a probability we sample, we choose this node, i.e. this is a probability we choose V times F of, sorry, the probability we choose, no, sorry, I did something wrong here. So again, what do we have here? So we have a function on the nodes, and AF is going to act as an averaging operator. So AF on the node V is going to be the average value of F on the neighbors of V, where we choose a neighbor based on this distribution, right? That's sort of three weights until it sums to a distribution, like choosing one of them, given the edge weight. And formally, so we choose a neighbor W with probability, this probability here. And then we multiply by F of W. So this is going to be, again, the average value of F on the neighbors of V. And again, the average is with respect to the distribution induces by the weights. So it's not with the uniform distribution. And so we're going to study this matrix A in this formulation of the transpose. Of course, spectrally they're the same. Transposing a matrix doesn't change its eigenvalues, so it doesn't make any difference, but it'll be more convenient for us. And in fact, we'll see that viewing adjacency matrices as averaging operators instead as of random walk operators is actually going to be very convenient for us. So even though spectrally they're the same, in the functional sense, in the way they operate, it's going to be a much more convenient way for us to view them. Okay. So that's going to be the way we're going to define from now on adjacency matrices. So it's a transpose, what we used to define before when we viewed them as random walk operators. But again, spectrally they're the same. And then finally, we're going to say that, so here's the definition. So maybe before that, I'll make maybe say some facts about this. So now they are not symmetric matrices anymore. Like, when we studied, regular graphs, these matrices were always symmetric, which implied nice properties of their eigenvalues. But I'm claiming that exactly the same properties still hold. So I'll just state this as facts. So let maybe G with pi E be a weighted graph. And let A be the corresponding adjacency matrix. then? Well, first of all, A is an eigendecomposition. Which basically means it has eigenvalues, eigenvectors, in exactly the same way that symmetric matrices have eigenvalues and eigenvectors. This is a generalization of that. The eigenvalues, its eigenvalues are real, and they still satisfy. The first one is 1. Everything is the same, we've seen before. And thirdly, when it acts on the right, lambda 1, 1 corresponds to the eigenvector, which is just a vector 1, which means basically that A times a vector 1 is a vector 1. So my claim is that it doesn't matter how it puts the weights. If we have a function that's all 1, and given a not look at the average of its neighbors, it's still going to be 1, right? It doesn't matter what weights we give them. When we average a constant function, we get a constant function. So this is another benefit of letting our matrix act as an averaging operator, because this eigenvector corresponding to the eigenvalue 1 is always going to be the constant 1 function. If you let it act on the left, which is what we did before, it will actually be the stationary distribution of this random walk, which is going to be not the constant 1 function. Everything would still work. You can make all the analysis work, it would just be a bit more cumbersome. So that's another benefit of letting these operators act on the right now instead of as an averaging operator. Okay? So transpose of what we did before. So again, I'm not going to prove this fact. It's just a basic fact in linear algebra. I mean, if you want to test your knowledge in linear algebra, you can try and prove that. But again, we can use this to define expanders. So again, a weighted graph G with a weight on its edges is a lambda expander if you know the maximum of lambda 2 and lambda n is at most lambda, exactly the same as we did so far. And also we'll see some applications we care about one-sided expanders. So this is one thing, and it is a one-sided lambda expander. If you know lambda 2 is at most lambda. So exactly the same definition as what we had so far for regular graphs. They directly extend to arbitrary weighted graphs with non-negative weights. So that's the last piece of the puzzle we need before we can define what do we mean by local spectral expanders. So again, are there any questions? So again, let's go maybe scroll back a bit. So the way we defined the adjacency matrix weights is again, so the weight of a given V, the weight of the entry VW is just the probability that out of the neighbors of V choose W. So it's going to be the weight of the edge from V to W divided by the sum of all the weights of the edges given V. So we can view A as an averaging operator, on the right. Just average the values of F on the neighbors of V. And we use this, we defined, we said that weighted graphs with these specific adjacency matrices have nice spectral decomposition, exactly the same as for regular graphs. And when they act on the right, the eigenvector corresponding to the eigenvalue 1 is just an all 1 vector. Okay, and then we use this to define expanders like for weighted graphs, not just for regular graphs. Okay. So notice the graph is not only we're not assuming the graph is regular, we're also not assuming the weights are 1. To be doesn't have to be regular, and also could have arbitrary weights. Okay, so we generalized our previous definitions in 2 ways. Okay, and now finally, we can define expanders, high-dimensional expanders. And there's actually going to be 2 ways we're going to define expanders. There's going to be a local way and a global way. So what would be a local way? So let me give maybe here 2 definitions. So definition 1 of local, we're going to call local spectral expanders. Or this one, let's call this local spectral expanders. So again, so let x pi be a d-dimensional complex. I'm going to say that it is a lambda local spectral expander if for every k with 0 and d minus 2 and every k dimensional face, if we look on, so we're going to look on the link of tau, that's going to be some complex, but we're just going to look on its first and second levels. So we're just going to look on the underlying graph of it. So if this, the underlying graph of x tau is a lambda. Okay. So again, let me repeat this definition. So we're going to look on all faces up to level d minus 2. We're going to look on the link. That's going to be a d minus k dimensional complex. But we are going to completely ignore all the faces of side 3 and above. So we're going to look on nodes and edges. And that's going to define some graph. And we require this graph to be an expander. So you see, if we just look on the bottom level on tau being in the empty set, then we just say that the underlying graph of this complex is an expander, which doesn't tell us anything about the structure of the high dimensional faces. So what this definition does is says, well, also require that as you go up the complex, well, locally at every step you only look on graphs. We never define it for complexes, but we require for all the possible graphs you could generate by going to a face and looking on the graph that it induces. Okay, so that's going to be the main definition of expansion that we're going to see. So this you can think of it as type of a global definition. Turns out you can ask for a weaker notion. Let's make another, let's call this, I don't know what, we didn't give a name in the note, but let's call them weak local spectral expanders. Which is going to be the same, but just for level d minus 2. So what is this weak definition? It says, well, we have this, which be complex. We're just going to look on basically faces of maximal degree, maximal size, so that they even induce a graph. So they have size d minus 2. And we're going to say just those should be expanders. We don't care about the lower level ones. So in some sense, you can think about this definition as saying, so here's another way of defining, given this weak definition, which is saying a complex of dimension more than 2 is a local spectral expander if all its links are local spectral expanders. And then you do it recursively, and you stop when you can't go anymore, right? When you're at dimension d minus 2. So this is equivalent to saying that X is this weak local spectral expander if all its links are. And again, for graphs, once we get to the graphs, we just use the graph definition of expanders. Right, so when we get to, so the difference between this weak definition and the what we're going to call maybe the strong or the standard definition is that we just look on the top dimensional faces, not on all the faces. So you can view this as sort of like a type of maybe a global definition. Oh, sorry. I don't know which one you want to call local, which one you want to call global. I'm not even sure what.
This is global in the sense that you consider the link of the empty set, which is the entire global complex. Right. So the first is global because you actually are considering global information with the link of the empty set. The second is strictly local. You are only looking at information on links of the complex. So the first definition is kind of both local and global, right? You do require things for links of all levels, but there's also global information when you look at the link of the empty set, which is just the graph underlying the full complex. The second does not contain this, so it's purely local information.
So here's the first thing that we're going to ask ourselves: are these definitions the same, or are they different? So turn out they're not the same, because if you just look at local information on links, and let's say you have something that's more than a graph, let's say three-dimensional complex, it could just be the union of two disjoint complexes, right? So, and globally, you can see, it's not even connected. But locally, if you just look at links, you either go to one or the other, but you never know in which one you're lying. But the first theorem, we're going to see that modulo this type of problem of not being connected, that's the only obstacle. So a graph that is this local notion of high-dimensional expanders, or only about the top faces, and in addition, it's connected, has to be the stronger notion of local spectral expansion. So maybe so let me not write this now formally. I'll write this formally in a bit, but for now, let me just write this here. So this is called the trickling down theorem. It says the following. This is by Oppenheim, and that's going to be an example of what's this local to global type of behavior in high-dimensional expanders. It says that basically if X is this, what we call this weak notion, is this weak local spectral expander, plus all links, graphs are connected. So we don't even care about their expansion. We just care that there are not two disconnected parts in them. This implies that X is this notion of a strong local spectral expander. So this should be very surprising, right? Somehow we try to get some notion of expansion of like lower dimensional faces from information about the top dimensional faces, and the only case where this does not happen automatically is if these graphs are not even connected, in which case they cannot even be expanders, right? And what Oppenheim proved is that basically that's the only obstacle. So we're going to write this type of the more formal version in a bit, but that's going to be a really useful theorem, because it's going to say that if I ever want to prove that some expander I care about, it actually some complex is an expander, it's enough to analyze the links of levels d-2, which are just graphs. And usually they're going to be much simpler than going to lower level faces that have much more rich combinatorial structure. And for them, we just need to prove they're connected, which is a very, very minimal requirement. So that's going to be a really important theorem. And I think also I made a typo here somewhere. Trickling down theorem. But then before going to the theorem, let me just give one example. I think so far we've seen all these definitions and it just seems too much, right? So I think it might be good, and maybe that's going to be a good place to end today. So maybe next class I'll actually give you write down the formal definition, the formal statement of the theorem, and we're going to start building our way towards proving it. But before that, I want to give you one example. That's going to be the last thing that we'll do today. So that's going to be what's called the complete complex. So if you think about graphs, so the complete graph is sort of the best expander you could hope to get, from anywhere to anywhere, just one edge. So also spectrally, like the best you can get, everything like the best you can get. It's just not sparse, right? We usually care about sparse graphs. It's not sparse, but modulo that, it's the best we can get. So the complete complex is exactly the same. It's the best you can get, but it won't be sparse. So what is the complete complex? So this is, by the way, also called the Johnson complex, which I guess is because Johnson studied it, or something related to the association schemes. But anyway, I think we'll explain the notation. So let's n be at least d at least 1. So we define what's called J and D. This is going to be a d-dimensional complex where, let's call this X, where XD, just all possible sets. Right, so you have all sets of size D, and also, of course, going down. For every K at most D, you have all sets of size K. And remember, we talked that complexes should always be weighted. So pi D is going to be the uniform distribution. So we just choose a random, completely uniform random set of size D. And if you go down, it's also going to be completely by symmetry uniform. So this implies, by the way, that pi K is also uniform for all K. So that's like the simplest thing, right? So you could actually, to that extent, ignore the weights. It's just, it's like the analog of a regular graph, right? Sort of everything is uniform, you have all sets. It's really nice. So let's see, is this going to be a local spectral expander? Well, let's see. What do we know about graphs? Let's first remind ourselves about graphs. So first of all, so recall graphs. So we denote by K, let's call it maybe another number, M is a complete graph on M nodes. And we've seen that its eigenvalues, it's a really good expander, and its eigenvalue, I think, is going to be something like 1 over M minus 1. Right, so it's really, really, really good. And now I'm claiming that we can use this fact to understand the eigenvalues of the complete complex. Why? So maybe that's first. Let's choose K between 0 and B minus 2. And let's choose tau to be some link here. What is X tau? So I claim X tau is going to be all this. So the nodes are going to be all the elements not in tau. And the edges are going to be all pairs that do not intersect tau. So that's going to be basically the complete, so let's say the first level of it is going to be all this V in N, so V is not in tau. And the second level is going to be all these pairs UV in N, where U and V are not in tau. Right? Because this is how we define links. Our complex contains all the possible sets. So the level 1 is going to be take all sets of size K plus 1, containing tau, and remove K from them. So just all the nodes, all the elements that are not in tau, and similarly for edges. So if you look at the underlying graph of X tau, it's just going to be the complete graph on all the elements not in tau, right? So the underlying graph of X tau, and by the way, underlying graph is just a different way of saying we look on this two-dimensional complex and ignore all the other dimensional faces, right, is the complete complex, so the complete graph on n minus tau. Right, and what is its eigenvalues? So its eigenvalues, so m is n minus k, and the eigenvalue is 1 over m minus 1, which is 1 over n minus k, 1, right? And now remember, this is for, so what we said is for, if you take any k-dimensional face, and we look at its underlying graph, it's going to be the complete graph on n minus k elements. So its eigenvalue, because it's a complete graph, is 1 over n minus k minus 1. But remember that we showed k could be anything between 0 and d minus 2. So when is this lambda the largest? When k is the largest, right? So lambda is maximized when k equals to d minus 2, in which case we get 1 over n minus d plus 1, right? So all this comes to show you that the complete complex, as long as d is not really, really close to n, has really good, eigenvalues. So it is a lambda expander, right? So the conclusion here, the example is the complete complex, and I have n elements and take all sets of sizes at most d, is lambda expander for this lambda. Lambda equals 1 over n minus d. That's one. Right, this is the conclusion here. So this example is mostly to make sure that you all understand the definitions. So we're almost out of time, so let me just summarize what we studied today. So today we mostly studied definitions, right? We didn't prove anything, but we defined many, many new things. We defined simplicial complexes, we defined links, we defined weighted simplicial complexes and weighted links. We discussed adjacency matrices for weighted graphs and how to view them as averaging operators. And finally, we defined two notions of local spectral expanders, one that is global and local, and one that is just local. We said that there is a theorem called the trickling down theorem by Oppenheim connecting the two that we're going to see next class. And we went through this example of the complete complex. But one thing that should not be clear completely at this point is, why is this definition useful? I mean, maybe we can prove the complex is a local spectral expander, but in what sense is it expander in a combinatorial sense? We're going to see that later in the class. So for now, you have to take it on faith that this is a useful definition. But we're going to see some connection to other more global definitions later on. Okay, so maybe now it's a good time to see if anybody has any questions before we conclude the class. So I highly suggest to people to review these definitions, in the notes before next lecture, so that you come prepared when you start sort of building all our tools towards proving Oppenheimer's theorem. Okay, so that's it for today. So let me stop recording.